Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We will continue with our module 9, that is the distribution network resiliency analysis. In the last class we have derived the fragility curve for different components in a distribution system, and today we will see the distribution network resilience against extreme weather, that is the hurricane or cyclone. It is the same thing when it is at the Atlantic Ocean, we call it hurricane. When it is at the Pacific Ocean, we call it typhoon, and when it is at the Indian Ocean, we call it cyclone. Okay. So, what is the effect of hurricane, cyclone, and how you can make your system stronger against those events for the distribution network. So, the impact analysis of hurricanes on distribution network follows few steps. First, take the historical hurricane data. Okay. Obviously, you will get the wind speed, what is the landfall angle, what is the track of that hurricane, that data you will get from your meteorological department. So, get that data, but you will get only, let us say, for hurricane Fani or Amphan, that only happened once, right. So, you will get only one track for it. So, only one data will not be enough for doing a probabilistic analysis. So, generate hurricane scenarios or synthetic data by taking that value and then plotting as an probability distribution function and generate multiple scenarios with the help of Monte Carlo simulation. Okay. So, then you have a bunch of scenarios for that hurricane, keeping one hurricane as the base case. After that, fit that value or fit that hurricane scenarios to the fragility curve of different components, because you have network. So, you have considered that how many poles are there, lines are there, substations are there, transformers are there, everything you have considered, and there you feed that your scenario of that hurricane or the wind speed, attack angle of the hurricanes, that data you feed in, and then check which portions of your network will fall down or will break down because of that hurricane intensity. So, from there you will get the system condition, and as well as by looking at that you can suggest that which portions of the network needs to adopt the hardening algorithm or hardening measures. Okay. So, hurricane data collection, which kinds of data you need? First, meteorological data, that is the wind speed and the gusts, that is the sustained and the peak. Central pressure of the storm, storm surge height and forward speed and the radius of the maximum wind. That is the meteorological data you need for the hurricane. Then storm track, you need the storm path coordinates over time, landfall location and the time, historical hurricane records, their intensity and damage, and return period or frequency for probabilistic risk assessment. That means, when the hurricane falls, at which location of the network it falls, that is the coastal area, let us say. Then if the hurricane, what is the frequently, what is how much frequently the hurricane attacks that region. We know that the Texas or the Gulf of Mexico region of the US, that is very prone for hurricanes. Even our India, the Bay of Bengal coastal area of the Odisha, Andhra and West Bengal, they are very prone of getting hurricanes at the rainy season. So, that how much frequently the hurricanes is attacking that portion, that you have to know for getting the probabilistic risk assessment. Then get the geospatial data, that is the topography and the elevation of that particular geography. Then land use and land cover affecting wind flow and the flooding. That means, how much trees are there, how many buildings are there, those details, or agricultural land or barren lands or ponds, what you have at a particular land cover. Let us say you have a long trees, big trees, that will slow down the hurricane obviously, or you have a big buildings. So, that will be an obstacle in front of the speed of the hurricane. So, how much land cover or which kind of equipment or infrastructure is there for that particular place, that will give you the geospatial area data. Then infrastructure exposure data, that is the location of the distribution assets, that means in the track of the hurricanes which kinds of assets are coming, how many substations are coming, how many poles are coming, how long lines are coming. So, this data you have to keep from the GIS map, and then critical infrastructure and population centers. That means where your users are located, okay, where they are clustered. This data you need for the infrastructure. So, now by keeping all this data, how to generate the synthetic hurricane tracks? As I have told that you will take a base hurricane, and then from there you will generate the multiple scenarios. So, input is the historical hurricane data, that is the track, speed, wind field and the decay rate. Okay. Whenever an hurricane enters the ground from the sea, it slows down. Gradually it slows down, not suddenly the speed will become 0, but as the obstacle is more and the land, so the speed will slows down the hurricane. So, select a base storm, choose a well documented hurricane as the baseline. Okay. Then what values you will take? Take the initial location, take the translational speed, bearing angle, landfall decay rate and the wind field radius. And these things you perturb a little bit to create the scenarios or to create the synthetic tracks, because that is a deterministic track, because that event has already been happened. So, you know how the hurricane has been traversed through the line from the coastal area. So, take that data, perturb it and generate the synthetic tracks. Use of storm evaluation model to simulate the tracks which each perturbed set. Take the perturbation data and then fit it to a climate adaptation tool developed by ETH Zurich. That model is very good for simulating the hurricane tracks. You can fit the input data there and you can generate your own synthetic hurricane tracks. Okay. Then store and validate, save the generated tracks, ensure they remain physically and climatologically plausible. That means they are feasible. It should not be that you generated some infeasible solution or infeasible scenarios. Then ensemble the synthetic hurricane scenarios to get the impact analysis. Okay. So, now you have to model the hurricane wind field. If you see an hurricane, the damage caused by the hurricane primarily results for the high intensity of wind. Okay, that is the main driving force of the breaking down your system equipments. Okay. These wind speeds are spread around the region of the hurricane's eye. So, if you see an hurricane, it has a center point that is called the hurricane eye, as you can see. Then at the hurricane eye, the speed of the hurricane is 0, because that is the center. If you go from the eye to the radius, or if you go outside of the goes towards the outside of the hurricane, then the speed gradually increases. Okay. And outside the hurricane, again your speed will become 0. So, the wind speed distribution changes along the hurricane's path as it moves inland and location of its landfall. So, at the landfall the speed will be very high when it enters the land, and then when it traverses from the land the speed will gradually decrease. So, that is the track speed. Similarly, the speed at the eye of the hurricane is very less, and if you go to the surface of the hurricane, then the speed will be more. So, depending upon where your facility lies, whether your facility is close to the eye or it is close to the surface of the hurricane, that will decide how much impacts it will impose on your component. So, static gradient wind field model says, first you have to see the few terms of it. First, maximum sustained wind speed, Vmax. What is that? This is the peak wind speed of the hurricane measured in knots, that is your 1 knot equals to 1.852 kilometer per hours, that is your nautical miles. Okay. So, this is the maximum sustained wind speed. Okay. That is the maximum speed that an hurricane have. Okay. So, distance to Vmax, that means let us say this is the starting, this is your eye. So, what is the distance to get that, or where you will get the maximum speed. Okay. So, this is the distance from the hurricane's eye to the point where the maximum sustained wind speed is found. So, if you go from the wind speed to the outer dimension, you will see slowly your speed is increasing, the hurricane speed is increasing, and at a certain point it reaches to the peak value, and after that it will again decreasing, and if you go outside the hurricane then it will be at close to the 0 value. Okay. So, this is the, you can say, maximum wind speed, and this is your distance RV max. So, radius of the hurricane, this is the radius from the hurricane eye representing the extent of the wind field. Okay. Means till that point you have the effect of the hurricane, that is your RS. After that your wind speed is approximately 0. Okay. So, this is your the common terms we use to model the wind field of the hurricane. So, representing that, if you see the static gradient wind field model, it is generally modeled as a piecewise mathematical function. Okay, because you have this region, then you have this region, and then you have this region. So, for an hurricane you have 3 regions. First, from the hurricane eye to the maximum speed point, then from the maximum speed point to the radius, then from the radius to the outside. Okay. So, there are 3 regions. Okay. So, depending upon that, if you it is from 0, that means I to the maximum speed point, then you can see the speed is increasing, it is an exponentially increasing, and it will be saturated at the V max value. This is your V max value. Okay. Then after that, from this RV max to the RS, that is the radius of the hurricane, speed will inversely decrease, exponentially decrease. That is this second term. Now, after you cross the radius, that means you are outside the region of your hurricane, then it will become 0. Okay. So, this is how you can represent the piecewise mathematical model for an hurricane. And when you simulate it, let us say when the hurricane moves through the power system, so you will see your component falls under which speed. That means your, let us say, a distribution poles comes to the radius of the your hurricane. So, we will see that this one is close to the eye, or it is close to the radius, or it is close to the RV max. So, depending upon that, you will decide the speed of the wind at that point, and that will say that whether your fragility curve, from that fragility curve you will get the value that the system is susceptible or durable or resilient or not. Okay. So, steps to evaluate the impact of the hurricanes on distribution network assets. First, get the hurricane tracks and wind field model. Okay. So, input is the hurricane track, latitude, longitude, time and the parameters V max and the RV max and the radius of the hurricane. For each point along the track, generate spatial wind field using the gradient wind model, what we already just studied. Then do the asset mapping, that means map the distribution network assets like poles, transformers, lines, substations and all the assets through this with this hurricane track. Like with the hurricane track or hurricane speed, see which assets are coming to that track. Okay. Then wind speed and interpolation. So, interpolate the wind speed from the hurricane model to each asset location based on the track position, time and their dynamic modeling. That means, see that component or that facility comes at which direction, how much distance it is from the eye of your hurricane, and from there you will get the wind speed it is facing, and from that wind speed what you have to do? You have to do the fragility curve assignment. Okay. Assign an appropriate fragility curve to each asset type and relate wind speed to the probability of the failure. So, from that wind speed you got your fragility curve that you have already studied in the last class. We will see the fragility curve, we got the wind speed, now you will get the failure probability. Okay. Then do the damage probability estimation. Compute the damage probability for each asset by inputting local wind speed into the fragility curve. Okay. Then do the Monte Carlo simulation. This you got only one value, only one wind speed you got, but it is not really that you will get only one deterministic value. This may be a probabilistic or a stochastic value. To get a wide range of scenarios, do this Monte Carlo simulation and perform simulations to account for uncertainties, wind speeds and the fragility parameters. So, perturb your wind speed or think of a mu and a sigma, plot it as a Weibull distribution, and then you will get from the Monte Carlo simulation multiple scenarios. Then with these scenarios get your failure probability for that component with the variation in the wind. Now, impact aggregation. So, you got multiple scenarios, summarize the total expected damage. The same thing we did for probabilistic OPF. You have to take the expected value of all the scenarios. Number of failures, outage areas, economic loss and restoration needs. Okay. Then you do it at the network level assessment. You got for each and every component what is the economic loss, if they are failing or not. Now, you put those data at the transmission or the distribution level. So, analyze how asset failures affect network performance. That means, if certain poles or lines goes out of order, then is there any backup facility for your system to restore the service, or your underneath areas will be completely become dark. Okay. So, do this study, do this analysis with this network level assessment, and then prepare the report for the final decision making. Okay. So, what are the how you will measure your resilience at your network? First measurement is done by expected outage duration. That means something happened in your network and you will see that for how many duration or how many time steps you are experiencing that outage. Okay? And it is given by this expression, which is actually expected outage duration at each and every load bus. You sum it and divide it by the daily peak load. Then you will see how much duration you have experienced your outage. Okay? The next thing is the system wide expected energy not served. First one is the outage duration and the second how much load you have not served for the total time period of your outage during the outage. So, that is calculated by the amount of load shedding. You sum it, take the average for every bus and do the summation for the total time period, and you will get the total a system wide expected energy not served because of a particular resilience event or a disaster events. So, you have few grid hardening options or the infrastructure upgradation options. What are those? Underground cable lines, we already talked about that. You bury the overhead lines to reduce the exposure of the wind, ice and trees. Stronger poles and towers by following proper standards. Wind restraint designs, take the hurricane rated hardware, like the designs there is some standards that follow them to make them more strengthened. Flood resistance substation building. Okay. Then you can use smart grid technologies like automated switch and the reclosures, that if something happens to avoid cascaded failure, that means only one, let us say one tower toppled down and one, you can say 2 or 3 lines has been broke down, but because of that fault, because that will create a fault, and because of that fault if in cascading scenarios happen, then other circuit breakers or the relays will also start tripping down, then you will see cascading failure. So, avoid that, you can have automatic switch and the reclosures. Advanced metering infrastructure, that will give how many customers are now living in dark or not getting electricity. Real time monitoring using the SCADA system. You can have system redundancy, that means loop distribution circuit. So, other than having only radial circuit, have few normally open switch that will give you a meshed architecture that will help you to reroute the power at the time of outage. Create small microgrids that will be that can operate in an isolated manner and give the backup power when it is needed. Okay. And then you have DERs in place, that is the solar batteries, your electric vehicles, to give a redundant energy supply, okay, at the local level. So, this is a typical grid hardening process, planning process. You have a network, now you want to make grid hardening. How you will do? You want to place few DGs or you can to select few lines to harden, or you want to place some switches to connect the weakly meshed to go for a weakly meshed connection. First, what you will do? We will first check what is the wind speed, take the fragility curve, then see in the network which are the most brittle or the most vulnerable locations in the network, then take the risk analysis and do the risk analysis, and then accordingly you place your DGs and the switches. Okay. Then we will do the optimal planning decision by minimizing the total cost and the total recourse cost. Okay. So, with this we do the planning purpose. So, you have to keep the objective function, the total planning cost will be minimized. That means you have only few options. Let us say you can install only 4 to 5 DGs diesel generators in all over the network. So, abruptly you cannot just place them. So, first you have to see which are the most vulnerable locations and which lines are most vulnerable, which are the most critical loads present. So, you have to always serve the critical loads. So, those things you have to taken into consideration with the proper stochastic model by generating different scenarios from your wind speed and your hurricane tracks, and then study it and then do the planning study. So, the few standards what we normally follow for improving network resilience, first you have IEEE standards like IEEE standard 1366, that is mainly used for enhancing the reliability indices. You have IEEE standard 693, that is designing for the substations against the earthquake resiliency. Then you have IEEE 1547 series that will tell you the interconnection of the DERs to support the grid resilience with the help of fault ride through analysis or the voltage ride through analysis or giving an islanding options. Then you have National Electricity Safety Code NESC designed by ANSI, which covers the design, construction and maintenance of the overhead and underground electric supply and the communication lines. Includes provision for wind and ice loading structure strengthened to clearance and requirement. That means this will give you how for a line how much wind and ice loading is permissible, and for making that whatever how much strength you have to give to that line and the tower, okay, and how much clearance you have to keep from the ground to the sag level. That means if this is your tower, this is your tower, this is your ground and this is your sag. So, this is your clearance. So, how much clearance you have to keep for the safety. Then you have American Society of Civil Engineers standard, which will say the minimum design loads for building and other structures, okay, to address the wind, snow, flood and seismic loads for the utility structures. Then you have ASCII manual 74, which is the guideline for electrical transmission line structural loading and used for reliability based design of power lines under extreme conditions. Apart from that, you have Federal Emergency Management Agency and National Fire Protection Association in the US. They also have few guidelines for the substation and control center design against the flood prone zones, for the flood prone zones, okay. And also NEPA 70 standards gives the covers the wiring and the electrical system safety, including the emergency systems. So, these are the common resources normally used by the distribution system operator after the post disaster restoration. That means, you can use the fault indicator and your real time controller and the communication facility to identify where the hazard has been happened, any fault or anything has been happened. Second, you have your DERs at few locations like your storage, your PV system, your diesel generator. So, you locate them and turn them on and then supply to the give as a backup supply to your critical customers. Other than that, you have repair crew that will reach there and start restoring the services, that building again the towers or your lines, and then you have mobile power stations that will be your ESS and the EV fleet that will go, and very low capacity, but that will go there and give an emergency backup supply for the customers. So, this is the overall distribution system operation planning, that before disaster, when you forecast the weather, that means you forecast the event, what you want to do is the expected value of the cost or expected value of the restored load, you want to maximize supporting or subject to the constraints of the decision variables and the constraints. Then after this happens, take that decision or the location where you have to move your mobile stations, take that location and do after the disaster that your maximization of the restored load amount. First you predict that how much maximum you can do, so you will get the route of your mobile stations, okay, the total capacity, how much you have to send and how many you have to send, where you have to send, those locations you have identified by the pre-disaster event, okay, keeping that your maximum load restoration is possible. Now, after the disaster happened, that is a real scenario that may be or may not be same with whatever you have assumed before the disaster. Now, after the disaster happened, you take that MPS location, that is a decision variable, and keep that at your algorithm as a constraint. Okay? After that, keep that as a constraint and see after the disaster, if you want to maximize the load restoration keeping those MPS location or the capacity constraint, then what kind of load reduction, network reconfiguration or DER dispatch decisions you have to take. So, with this, after the disaster strike, the damage assessment and the restoration services are carried out for a distribution network. With this, I will end today's lecture and we will continue with this resiliency study in the next class. Thank you.